All right, this is an example of multiplying radicals, but they're specifically square roots. There's actually two ways you can do this problem. I like to do it this way. I go ahead and I multiply the square root of 5 times the square root of 10 and say that's the square root of 50. And then I simplify my radical the way I did in previous problems. I look at the 50 and I'm like, okay, I need a factor of 50 that is square rootable. That's what I like to call it, square rootable. That's an Aprillism. It's not in any textbook. And I know 25 is a perfect square, just to remind you of your perfect squares. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared, 6 squared, 7 squared. I could go on squared, but I know that 25 is a factor of 50. So I would break this down to be the square root of 25 times the square root of 2. And of course, the square root of 25 is 5, because 5 squared is 25. And so that would give me 5 times still the square root of 2, because you can't take the square root of 2. So this is leaving it in radical form, simplified radical form. Now that's just one way to do it. Another way to do it is to break down the 10. 5 is a prime number. I can't break down the 5. That's just the square root of 5. I mean, I suppose you could write the square root of 5 times the square root of 1, but the square root of 1 is just 1. And 1 times the square root of 5 is still the square root of 5. So I'm not getting anywhere with that. If it's a prime number, just leave it alone. But the 10, I can break the 10 down to be, it's a different color, the square root of 5 times the square root of 2. And then if you look at the square root of 5 times the square root of 5, that's really the square root of 5 squared. The squared cancels out the square root sign, so you're just left with the 5. And still the square root of 2. So there you go. It works both ways. Whichever way makes more sense to you. I don't really know of another way to do it. So yeah, for that one, that's it. That's all I got.